So for the first part, you need to be able to show how you found your vertex and axis of symmetry algebraically, or at least the setup of it. Axis of symmetry formula is x equals negative b over 2a. Green phone up. So to find our axis of symmetry for number 1, we're going to do that same thing. Remember that each of these is a number, a, b, c. So for our axis of symmetry, this would be x equals negative 10 over 2 times negative 1. What would that axis of symmetry be? So let's just say that one. 5. But x equals. So make sure you always have x equals with these. Don't worry about that. Because we don't need that to find either of these. And then for the vertex, to find the y value, we're going to take that x and put it in for all of your x's in the equation. And after you show that setup, you can do it by hand or in the calculator, it doesn't matter. What would that y value be? Say that again. So then your vertex would be, as an ordered pair, 5, negative 3. So the work you could do in the calculator or by hand, but you have to show the setup. Questions on that before we do number 5? We're going to start off the same way, finding the axis of symmetry for number 5. So that would be negative 4 over 2 times negative 1. What would that axis of symmetry be? Positive 2, x equals positive 2. So you're going to put that in the middle of your table and fill out the rest of your x's. Go backwards and forwards. And then in your calculator, you're going to put in this equation into y equals. So go ahead and do that. I forgot I need one of these. Yep, just fill out the table from those 7 numbers. We have negative 9, negative 4, negative 1, 0, negative 1, negative 4, negative 1. Remember that they should repeat, and in the middle, this would be the middle, and then they repeat on both sides, and then you can go ahead and graph those points. Your vertex is going to be that point in the middle, the 2, 0. Your domain, you're looking left to right. Imagine this keeps going down and right, so it keeps going left and right, so that would be all real numbers. You can choose how you want to write that, either in interval notation or in set builder notation. The domain for your quadratics will always be the same, all real numbers. The range will be different depending on which way it's facing. And the y value from the vertex will help you with the range. The lowest, this keeps going down to negative infinity. The highest is going to be that same y value, 0. In interval notation, that would be a square bracket because that's a closed point, or everything less than or equal to 0. The zeros or x-intercepts, where does it cross the x-axis? There's only one place at 2. And this needs to be in curly brackets, whether there's 2 or 1, but it would just be x equals curly brackets 2, the number 2. Do you have any questions on how we find any of those characteristics or how to graph it? Go to the next page. Or to the back of this, sorry. So this is still 10.1, graphing exponential functions. We'll do one of these for sake of time. Which would we like to see? Number 4, okay. In number 2, cross out the end behavior and asymptote, because I meant to do that, but didn't. So with number 4, I need a table in order to graph these. We're going to start with the same 5 values every time you get an exponential function. -2, -1, 0, 1, 2. Whether we can use those points or not will depend on the numbers we get in the table. So in your y equals, go ahead and type this equation in. Make sure you use parentheses and make this into a fraction. And then the caret, top hat, whatever you want to call this, for the exponent. And then bring it back down. And then go into the table. Now, at those 5 points, you have really big numbers. 130, 66, 34, 18, 10. I'm still going to write those down. But the only one I can really graph out of all of those is the 210. And I want 3 to 5 points on this graph. So I'm going to find some others. And just look at 3, 4, 5, 6. So 6, 4, 3. That way I have more points to plot. And then I'm going to plot these 5. way you can kind of see where the curve is or where it starts. If you kept looking on your calculator, you'll see that these are all fractions, and eventually it gets closer and closer to 2. It's not actually at 2, it's just, you can only put so many decimals in here. So domain is going to be the same as the quadratics, all real numbers. The range is going to start at where it gets closer and closer to, so 2. And then it keeps going up to positive infinity. And then that would just be greater than 2, not equal to, because it doesn't actually touch 2. The calculator is deceiving. What's the y-intercept? We do. So even if you can't plot it, it's good to still have those first 5 because you can easily find the y-intercept. Have any graphing exponential questions? We're going to come back to curve of best fit. Look at page number 5. And we can do a few problems here if need be. What problems do we want to see to go over on this video? 15. So 15 is nice because it's already in factor form. So we just have to drop the parentheses, set each one equal to 0, and then solve. So 15 is probably the easiest form. 16 is a little bit more than that. When you have an x minus or an x plus a number, it's always going to be the opposite. So you could actually solve this, or you could just say this is going to be 1 and this is going to be 8. And then write your final answer in curly brackets and these series. What other questions on this page? Okay. So with any problem that doesn't look like 15 or 16, you want to make this equal to 0 if it's not already. So move 5 over. And then see if we can factor this. Can we factor this? And using what? Difference of squares, yeah. So what would those two factors be if I split that? 5x and plus 2 minus 2. And then because these are going to give you the same number at the end, just one's going to be positive, one's going to be negative. You could do both, you don't have to do both. Still set both up. But you really just have to solve one of them. And then I know this is going to be negative 2/5 and positive 2/5. So So you can write them out separately or write them as plus minus 2 this. Other questions on this? Then you can either look at the previous page for the curve of best fit or the next couple of pages. 10.3 is the only one you can use Desmos on, so if you would like an iPad, you can have one. And which of those would you like to see do go over? I would say just look at 6 and 7 for right now, or page 3. Number 6, or page 6.
Oh, yeah.
Number 6 on page 7. Okay, so in this we're given some table. It's asking us, is this linear, quadratic, or exponential? One, we're not dealing with linear, so you could just cross it out. So it's going to be quadratic or exponential. If you have anything with years, you want to change those. The first one to 0. The next, all of the rest to how many years has it been since the original. So from 60 to 70, that's 10. 60 to 80, that's 20. 30, 40. Remember, don't assume that the pattern will follow. Actually count how many years has it been, because it may change. It may not be a pattern. And then I'm going to do this in Desmos, but if you want to see it in the calculator also, I will go back and do that. So then we would put in each of those numbers. Your equation becomes some big equation because of the years, and it's just easier to choose it. So when you hit the plus, you can see what it's doing. And I'm just going to put in both, and then we'll see which one is a better fit, and then we'll talk about which one would be a better fit in the context of the problem. So your two equations for Desmos, think about your quadratic equation, but change your x's and y's to x1, y1, the equation to tilde. And the equation for the exponential y equals a times b to the x, but change it again. So I'll type in both y1 tilde ax1 squared plus bx1 plus c. And then the other one, y1 tilde a times b raised to the x1. If you're not sure, like this looks like it could be either, just based on the graph. But when I look at the data, I'm looking for whichever one goes through it the best, is closest to 1, which would be the quadratic. Actually, let me make sure that's accurate. Yeah, okay. There was one that I did yesterday that it was similar. But whichever is closest to 1, use that. If they both happen to be 1, think about the context of the problem. So in this, we're looking at population over a span of years. Sometimes, depending on the year, depending on the climate, depending on the environment, it could go up and down. Sometimes it could just grow. So you have to think about, would this just keep growing, or could it go up and down? And in this case, because it can go up and down, quadratic would be the best of it. So then we would say model is a quadratic. The equation, we would use this. It doesn't say what to round to, so let's say 3 decimal places. So 0.031 x squared plus 0.06 is the round. X plus 50.951. And then we're looking for what would the approximate population in 2020 be. So one, we need to know how many years would that be from 1960. So then we're going to type into Desmos x equals 60. And find where those two lines cross. $165.62, and that's in thousands. Remember, if it's asking, if it wasn't in thousands, that couldn't be a decimal, but because this is 165.62 thousands of people, that's okay. The decimal's okay. Did we want to see this in the calculator? Then I will give you the rest of class today to work through, keep working through the review, come see me with any questions. If you want to keep working on your Unit 9 tests, you just have to make sure your phone is put away and you can come see me to do that. Remember that you can also come see me after school today or tomorrow to work on your Unit 9 test, but tomorrow will be strictly Unit 10 unless you finish it.